UC Berkeley professor of astronomy Geoff Marcy is one of the pioneers and leaders in the discovery and characterization of planets around other stars. His research results include detection of the first multiple planet system, the first Saturn mass planet, and the first Neptune mass planet. In recent years, Professor Marcy's research has focused on the search for Earth-sized planets around other stars. He is a co-investigator of Kepler, the NASA spaceborne telescope dedicating to identifying Earth-like planets and potentially helping to determine how many of these planets fall in the habitable zone with the potential for supporting life. What properties of another planet are necessary for intelligent life on them? And what is the evidence for or against intelligent life? Here to answer these and many other equally compelling questions is Geoff Marcy. Please join me in welcoming him to the JCCSF.
Well, it's a real pleasure to be here. Thank you all for coming out. I feel that this is a special year because it was just 20 years ago, in 1995, that we humans had no evidence of planets around other stars at all, nothing. And so for all of the existence of we Homo sapiens on the planet Earth, humans were wondering whether or not there were other planets around the twinkling lights. And I'll try to give you some sense as to how far we've come in the past 20 years now. To bring you all up to speed, I'll remind you that when you look into the night sky, you see with your naked eye hundreds of stars. With binoculars, you see thousands of stars. And with the most powerful telescopes on Earth or above the Earth's atmosphere, you find out that we live in a galaxy of 200 billion stars, a pinwheel of stars called the Milky Way galaxy. And so it's a logical question, since we know that those stars are kin of our sun, some of them being larger than our sun, some smaller than our sun, nonetheless suns in their own right. Are the 200 billion stars in our Milky Way populated with planets that orbit them, something like the 8 major planets that orbit our sun, and maybe smaller planets and asteroids and comets and so on? Or not? Is there something special about our own solar system with the sun and our 8 major planets, something that allowed us humans to spring forth, but some property, the planets, the Earth itself, that make us somehow special? So when you look at the Milky Way that you can see with your naked eye and sense the billions of stars, the question has loomed since before the time of the Greeks, whether or not the Earth was unique. And we're beginning to answer that question, but it's a profound one, because the only signs of life we have anywhere in the universe is the life right here on the Earth. Still to this day, in 2015, there's no evidence of biology of any sort anywhere else, not on Mars, Jupiter, Saturn, or outside our solar system. So the search for habitable planets like the Earth and the possible life on them remain major quests, I would say, in science in general, and sort of a part of our culture to find out our place in the rest of the universe. So how common are Earth-like planets in our Milky Way galaxy, and how would you search for them? Well, starting about 20 years ago, a few of us, myself, a colleague of mine in Geneva, Switzerland, we began searching. And it was difficult. We finally found a Jupiter-sized planet about 20 years ago, 2 more, and then by 1996, middle of 96, we had maybe a half a dozen of these Jupiter-sized planets. But that's as much as we had 20 years ago, starting from nothing. And now we've proceeded to ask the question about Earth-sized planets. How would you search for an Earth-sized planet around any of the stars that you see there in that picture of our Milky Way galaxy? Well, it turns out there's a powerful new technique that a handful of us worked on. Bill Barucki was the real pioneer at the NASA Ames Research Center. And the idea that we came up with was watch the brightness of stars, and when an Earth-sized planet happens to cross in front of the star, then that Earth-sized planet blocks a little of the starlight, and you can make a graph of the brightness of the star over the course of time, see the star dim a little and re-brighten as the Earth-like planet goes around and around that star. It's a very simple technique. A kindergartner can understand that when a bug lands on a light bulb, the room dims. When a planet crosses in front of a star, the star dims, and we should be able to detect that. Not from the surface of the Earth, because we live our lives beneath the swimming pool of the Earth's atmosphere, so we have to go into space. And we designed a telescope to go above the Earth's atmosphere. It's called the Kepler telescope. Here you see it at Ball Aerospace Corporation in Boulder, Colorado, being assembled, solar panels, the actual there's a lens up at the front, a mirror down at the bottom, and the light comes to a focus from the stars at a digital camera. And the idea was to simply take pictures of thousands and thousands of stars, minute after minute after minute after minute, looking to see if any of the stars dimmed momentarily as an Earth-sized planet crossed in front of the star, blocking a little of the starlight. So we had to launch this into space, and it was quite a moment because this was 10 years in the design, engineering, and construction. And so the moment of launch about 5.5 years ago, a little more than that, was a nerve-wracking one. Those of us on the team flew out to Florida to the Kennedy Space Center. We sat there by the beach about a mile away from the launch site, hoping that the Kepler telescope would successfully launch into space. The telescope was placed in the nose cone of a Delta II rocket, which is a common rocket to send equipment up into space. And this is what it looked like at the moment of launch, but we were very worried. And I'll tell you why. The previous launch, the rocket went up and it went into the Atlantic Ocean. It was a terrible disaster, but some of you may know about it. It was called the Orbiting Carbon Observatory to measure the amount of carbon dioxide in the Earth's atmosphere. So the very previous launch had failed, and there we were now next in line. So I thought you might like this, I brought with me a video of the launch, actually 2 videos, and it's your choice as to which you might like to see. I have the official NASA version of the launch. And then I also have some home video taken by some people on the beach who were watching it. So which one? All right, you're persuasive. Here is the home video of the launch of the Kepler telescope.
15 seconds.
Oh my God.
T-minus 10, 9,
Oh my God.
8, 7,
Oh my
6, 5,
Oh my
4,
God.
3.
Oh my God.
Oh my God! Oh my God!
I can't believe it. It's so surreal. Oh my God.
You go, baby! You
Go, baby!
Oh shit! Oh shit! Oh my God!
People get so emotional about these simple launch. I don't know why they can't control themselves. But we had tears running down our eyes, hairs standing up on the back of our necks. We were all crying to see this telescope go up that we had been working on for 10 years. It is up successfully. It's still working to this day. The Kepler telescope is in a solar orbit around our sun, trailing behind the Earth. And it had an amazing mission, which was to simply take snapshots of a portion of the night sky in the constellation Cygnus. And here you see the constellation Cygnus, this star, this star, this one, this one, this one, and this one. Obviously a swan. So there's the Cygnus constellation, and here's the patch of sky that we were observing. Every minute taking a snapshot, recording the picture, and looking to see if any of the 100,000 stars in the field of view dimmed momentarily and then re-brightened. So I thought I would show you some of the data that we got from the Kepler telescope. This is again the field of view. These are the light detectors, so-called CCD light detectors. One star I'll just show you as an example, Kepler 10. It's at the center of that circle. And here I thought I'd share with you the actual data that we take. This is a graph of the brightness of the star Kepler 10 over the course of about 200 days. And if you look, we've done something clever here. The average brightness of the star has been set to 1. And we've scaled this so that this tick mark is 0.9995 of the average brightness. So the amount of dimming down to this tick mark is only 5 parts in 10,000, a very tiny amount of dimming. And you see the data points scatter around. That's noise, those are errors. As good scientists, we like to acknowledge, indeed highlight the uncertainties, the errors. This is all fuzzy noise. But if you have good eyes, you might be able to see over the course of the 200 days a repeated momentary dimming of this star Kepler 10. You might be able to discover the planet crossing in front, blocking the star. Can you see it by any chance? You have to look pretty carefully. For example, right here is a drop, and then over here is another drop. And then equidistant in time, another and another. And if you go back in time, there was one there and one there. So in fact, there is a planet orbiting, we have students do the analysis, by the way, so you're sharing in the joy that the students at Berkeley get to do in hunting for planets. Here are the data again, and there indeed is the evidence of the planet, regular, like clockwork, as a good upstanding planet should do, go around the star like clockwork. And so you can see again the original dimmings and then the repeated dimmings. You might say any one of them is almost buried in the noise, but it's the repeatability that makes it clear that it's an orbiting planet. You can even guesstimate just in your head how large that planet must be, because this planet, you see, dims the star by about 0.0005 of the normal brightness of the star. So it's a pretty small speck of dust that would just block that tiny fraction of the light from the full circular disk of the star. Now, that's not all, because if you now zoom in on these data, let's say that green patch there, here's the zoom in, here's the original plot that I showed. Here's the zoomed region in green. There you see one of the dimmings that you already discovered by your eye. If you look carefully, you might be able to see a second set of dimmings from another planet. It's a little difficult. You see, there's a dimming there, barely deeper than the noise. There's another and another and another and another, and the same going back in time. There is, in fact, a second planet orbiting this star. It's obviously smaller in diameter because it blocks less of the starlight than did the first planet, which was already a fairly small one. This one's even smaller. It's about the size of the Earth, a little bit bigger. And so this is interesting in many ways. It's a star that has at least 2 planets that we know of, the second of which is so small that you can calculate its size being about that of the Earth. This is an artist's rendering. We have no picture of the planet, of course, at all, but we know how large it is relative to the size of the star, which is sun-like. Here's the orbit, which we know well because we know how long it takes the planet to go around the star, the orbital period. That we know accurately, so we know the size of the orbit as shown here. Size of the planet, size of the star, all dimensions to scale. So this is pretty exciting. It begs a question, though. If it's an Earth-sized planet, approximately, is it rocky like the Earth? Does it have a hard surface? Or does it have a thick, gaseous atmosphere or envelope like Neptune and Uranus, maybe a very thick gaseous hydrogen and helium envelope like Jupiter and Saturn? The way to find out is to measure the mass of the planet, the bulk density of the material of which the planet is composed. And to do that, we make a different measurement. We watch the star, and the star will wobble around being yanked on by the gravitational pull by the planet. The more massive the planet, the more strongly it pulls gravitationally on the star. So we actually watch the star with telescopes on the ground, and the largest telescope in the world is the Keck telescope, located in the Hawaiian Islands on the Big Island. Some of you may have even gone there. It's located high atop a hopefully dormant volcano called Mauna Kea. And at the Keck telescope, this is a telescope with a primary mirror 10 meters across, a first down, a tenth of a football field. We take our students there, by the way. It's one of the joys of being a professor is that we can pass along our knowledge to the students, but also teach them how to use telescopes, analyze the data, and so they have quite a time going to the telescopes. In fact, I'm going to take a bunch of my students in June to see, that haven't been there, to see the Keck telescope and participate in using it. So this is part of the, the ongoing process, generation after generation, passing along the technical and scientific knowledge. So, does the star wobble, and can we measure its mass? The answer is yes. We saw the star wobble. We measured the mass of the planet, remember, as it yanks gravitationally on the star from watching the star. And we ascertained that indeed the planet has a density greater than that of the Earth, 8 grams per cubic centimeter, if you're interested, rendering it for sure rocky. It is a rocky, Earth-sized planet in a very tight orbit. One side of the planet blowtorched hot because of its proximity to the star. The back side of the planet dark and cold because it's not facing the star. NASA animators made an animation of this planet because it is Earth-sized and interesting. There's the sun-like star, the orbit of the planet. We detected it, as you now know, by the dimming of the star when it crossed in front. So there's the planet in silhouette in front of the star. The geology of the planet is unknown, but it may well look something like this with a rocky surface. How rough it is, how smooth it is, volcanism, we don't know. The NASA animators have added these white flecks that you see. For reasons I have no idea. Absolutely no clue why they thought white flecks would be a good idea in this. But you see, they did do something interesting. We don't know the geology, and it's possible there are canyons, there could be mountains, valleys. You see, the NASA animators watched Star Wars too many times. But it's a fascinating new field of geophysics. What is the geology of a planet like this? How does its surface deform? Is there plate tectonics? Is there a mantle underneath? Are there volcanoes? Is there perhaps an atmosphere? Is there a ring around the planet where the temperatures are lukewarm, suitable for biology? We don't know. So there are many questions outside the realm of astronomy, but in other science fields that are being spawned by these Earth-sized planets that we're discovering. Now, this one is in very close. I didn't mention it takes about a day for this planet to go around its star. It's hugging its star very closely. Happens to be the first one that we found with Kepler, but we've found many other Earth-sized planets, and I wanted to introduce you to 3 of them, 2 around one star. This is Kepler 62. Here again, you're seeing the brightness of the star over the course of time. You see the dimming. These blue lines are the data points with the error bars shown. The dots are the original data points. And you can see the star dim and re-brighten as a planet crosses in front. Same star, different planet. Both are the size of the Earth, roughly. The first one has an orbital period of 122 days. 1 year for that planet is 122 days. The second planet, the orbital period 267. So that's an orbital period almost as long as that of the Earth, 365 days. So we're finding Earth-sized planets that are orbiting their star, taking about as long in their trajectory as the Earth does, going around the sun, and therefore their distance from their host star is similar to the distance of the Earth from the sun. So that's very exciting. And of course, there's an underlying theme that I'll come back to. The farther a planet is from a star, the colder it is. It's receiving less and less heat from the star if it's farther away. And so these 2 planets with orbital periods of 122 and 267 are closer in to their star than the Earth is from the sun, but not so much so. So the temperatures on these planets would be warm, but not blazing hot. Here's a sketch of this Kepler 62 system. I've mentioned 2 planets, but I didn't tell you that there are 3 others. So this is a star, Kepler 62, with 5 known planets. You see them sketched out here, 1, 2, 3, 4, 5. And this green domain here is the domain where the planet would be far enough from the star that it would be at a lukewarm temperature, where the water, if any, and we don't know whether they have water, would be in liquid form, not so hot close in that the water would be in steam, boiled away, and not so far away that the water would be frozen into ice. But the habitable zone is where the water would be liquid, and of course liquid water is crucial for life as we know it anyway. And here's our own solar system for comparison. So we're beginning to find multiple Earth-sized planets around certain stars. And here's a little sketch of one of the 2 Earth-sized planets in the habitable zone. Does the planet look like this? I have no idea. We don't have 1 photon from this planet. All we know is how big it is and how far it is from the star, what kind of an orbit it's in. Here's the other of those 2 planets. Again, the size of the Earth, whether there are clouds, continents, oceans, peninsulas, we have no clue. Some people ask me, what's the most Earth-like planet that's ever been found? And here it is. It's Kepler 186. We announced it about a year ago now. Kepler 186F, planet F. You see the sketch here, the star, multiple planets. Here's F smack dab in the lukewarm habitable zone. Here you see where the star is in a star chart. You can look at it yourself with a telescope. And it's a planet that's about 10% bigger than the Earth, but at a temperature very, very similar to the our own Earth's temperature. So this is a very exciting planet. There could well be biology taking place. Maybe there are oceans and biochemistry occurring, and the onset of life might have happened on this planet, or not. I mean, we really have no idea. So here's an artist's rendering of this favorite planet. And I'm always a little, how shall I say, embarrassed and nervous about showing pictures like this because, again, we only know the size and the orbit that the planet's in and hence the temperature, but we don't know whether it has any of the surface features that you see here. There are, however, other planets that we do know about around this star from the other dimmings of the star. So it is in a family of planets. Now, I want to take a moment here and tell you what I think is the most exciting scientific result to to come out of Kepler. I've given you a sense as to what the Kepler telescope has found. But now I'm going to be a little more quantitative, if you will bear with me. This plot is a little complicated. It's a histogram, but I'd love to walk you through it because this is the heart of the result from the Kepler telescope. What you're seeing is a graph, if you can bear with it, the fraction of stars that have planets of different sizes. 1 is the size of the Earth, 2 is twice the size of the Earth, 4 is 4 times, 8 times the size of the Earth, 16 times the size of the Earth. Again, we can easily measure the size of the planets from the amount of dimming of the stars. And what you see here very clearly is that big planets exist, the size of Jupiter, but they're rare. 1 in 10, 1 in 20 stars has these big fat planets like Jupiter and Saturn. But as you consider smaller and smaller planets, there's this domain in here between the size of the Earth and 2.5 or so times the size of the Earth, where there are lots of planets. The Milky Way galaxy is rich with planets approximately the size of our Earth. It's an amazing discovery. We didn't know this until about a year ago. It's a really profound result. When you look up into the night sky, most of those stars have planets that are the size of the Earth. And this highlights that same point. In blue are the two domains in the histogram between the size of the Earth and twice the size of the Earth. And if you add up these numbers, 12% and 14%, you see that some 26% of sun-like stars has a planet between the size of the Earth and twice the size of the Earth in distant orbital distances comparable to that of the Earth. This is an amazing, I think, historic discovery. It's, for my money, this is, a fifth of an Armstrong step. It's a fifth of the invention of penicillin. It's something momentous that we humans, with our brains, have figured out that the galaxy that we live in has billions of planets the size of the Earth. So this is an amazing result. We actually know a little bit more. We can make the same kind of a graph, the fraction of stars that have planets versus their orbital distance from the star. Some of the planets are farther away from the star, the host star, than other planets. And this graph, don't worry about the details, shows you there are plenty of planets at all distances. There's no fall off. So there are planets far from the star, close to the star, and in the habitable zone where the temperatures are just right. And this is a little animation that shows this in summary. With Kepler, we looked at the Cygnus constellation, star after star. Many of them had a planet the size of the Earth. Some of those Earth-sized planets were located too close to the star and therefore were too hot. Others far away and too cold. But some of the planets were in the Goldilocks habitable zone with a temperature just right for life. And when we did the statistics, we found that about 1 in 5 of all of the stars we observed with Kepler, about 1 in 5 of them has an Earth-sized planet at lukewarm temperatures. So when you look up into the night sky, when you walk out of here this evening, you can look up at the twinkling lights and count 5 of them, 1 out of the 5 has a planet very close kin in its size and temperature to the Earth. Now, do they have liquid water? We don't know. Do they have life? We don't know. Microbial, intelligent? We don't know. There's another way to look at this. You can say, well, okay, in our Milky Way galaxy sketched here, how far away, how many light years away is the nearest Earth-like planet? If our great-grandchildren design propulsion systems that can take us in rocket ships to the nearest stars, how far away is the nearest lukewarm Earth-sized planet? Well, we can sketch that out now because we know the statistics well. We live in the, suburbs of our Milky Way galaxy. We can illustrate this by shrinking our Milky Way galaxy down to the size of the United States. And when you do that, of course, we live still in the suburbs. Here we are. There's JCC San Francisco right there at the tip of the arrow. And we can then ask, how far do we have to travel across the United States, one direction or the other, in this scaled down version of the Milky Way galaxy to get to the nearest Earth-like habitable planet? And the answer is, if you're here, the distance you have to travel in this scaled down Milky Way galaxy, the size of the United States, the nearest habitable Earth is across the Golden Gate Bridge. A stone's throw, essentially. And so, of course, this is consistent with this 1 in 5 idea. The nearest, there are plenty of stars within a few light years of us. 1 out of 5 of them has an Earth-like planet. So this is a very exciting discovery. It gives impetus, I would say, indeed, to the next generation and the generation after that and after that to build propulsion systems that can take us to the stars and perhaps acquire snapshots, data, maybe even see signs of life on those Earth-sized planets. Another thing that Kepler did, which is pretty mind-boggling, we didn't expect this, is that it has found many stars with multiple planets, families of planets around the host star. The poster child is Kepler 11. We found 6 planets, all of which dim the star, allowing us to detect them. Here's a sketch of Kepler 11. My graduate student, Lauren Weiss, is studying this system right now, writing a research paper measuring the masses of the planets as well as their sizes and densities. This is what the system looks like compared to our solar system. If you could fly in a spacecraft up to Kepler 11, it would look like this. The star would dim oddly over and over and over again due to this multitude of planets that all cross in front of the star, blocking the starlight at odd times as they go around in their clockwork-like orbits. So it's exciting to see families of planets that remind us of the system of planets we enjoy here in our solar system with the 8 major planets. It turns out we have found quite a few of these, and it's almost an embarrassment of riches. Here is a sketch of all of the multi-planet systems, 2 or more planets around individual stars, that we have found so far with Kepler. There are over 400 of these multi-planet systems, and you see them here. For each one of the planets around their star, by the way, we've scaled up the size of the planet so you can see them here. For each one, we know the sizes of the planets. We know the sizes of the orbits, of course. And we even know where the planet is in its wandering around the star, because we know when it blocks the starlight and goes around in its orbit and blocks the starlight again. We can, in fact, predict into the future where that planet will be at every instant of time. And let me show you now the prediction of where all these planets will be in the future. Please don't laugh, this is science. There are more multi-planet systems than we have astronomers to study them. It's a little like that, for those of you old enough to remember, the I Love Lucy episode where she was supposed to do quality control of the chocolates going down the conveyor belt. We don't have enough astronomers to do the study of each one of these planetary systems. And of course, for graduate students, it's a field day. They can do their PhD thesis studying one or a handful of these multi-planet systems, learning more about them. It's really a new era for humanity that we know about these other planetary systems that remind us of our own. Now, for the remainder of the talk, I'd like to turn my attention to a topic about which I know nothing. And so I'm going to issue a warning about my ignorance. I'll try to tell you as much as we do know. Don't laugh at me. Okay, you can laugh. The question that I'm going to give you a sense about is, have we learned anything in this about the prevalence of intelligent life in our Milky Way galaxy? Obviously, we don't have any detections, there's no empirical evidence, but we know more about how many Earth-like planets there are, and hence we can begin estimating how many planets might harbor life. You can do the calculation yourself. 1 in 5 stars has an Earth-like planet. Out of 200 billion stars in the galaxy, that tells you right away there are some 30 or 40 billion planetary systems that have an Earth-sized planet at lukewarm temperatures. They may well have water. And you can ask the question, what fraction of those Earth-like planets might harbor an intelligent civilization? Is intelligent life a 1 in 10 throw of the dice? 1 in 100, 1 in 1,000? Well, the most pessimistic guess I've ever heard is that maybe intelligent life only happens on 1 in 1,000,000 of the habitable planets. Well, then you can do the math. Because if only 1 in 1,000,000 habitable planets has intelligent life, but you have 30 billion of those throws of the dice, you can see right away that there must therefore be thousands of intelligent civilizations scattered throughout the Milky Way. Some of them sprang up thousands of years ago, millions of years ago, before we humans walked the face of the earth. And so some of them have technology that's 1,000 years or 1,000,000 years more advanced than our technology. So that's pretty exciting. I always think about this because I always think about my iPhone, and I'm one of those people that likes to get the next generation iPhone, iPhone 4 and then 5, 5S, 6. I'm guessing that these advanced civilizations have an iPhone, 4,298. And whether they work as phones, I don't know. I bet they don't. Mine still doesn't. But the question arises, did science fiction get it right? We now have done a back-of-the-envelope calculation. You just saw it, predicting thousands of advanced civilizations. Are the Romulans and the Klingons out there? And of course, we've just calculated that it seems likely, even in the most pessimistic estimate. But is this right? And here's where I'm going to suggest that probably most of you have a split brain. Half of your brain is saying, of course there's life out there. There are all these planets. How could there not be intelligent life out there by the thousands? But I bet that the other half of your brain, the skeptical half, looks up into the night sky. It looks pretty dark. There's some stars out there. We have powerful telescopes. Where's the evidence of this Milky Way galaxy teeming with intelligent critters? Are they really out there? Do we really live in a galaxy with intelligent folks floating around in spacecraft as depicted in science fiction novels and movies? Well, this is a problem. We actually harbor both ideas in one brain. Must be life, give me a break. And so we really do have a question, and part of the reason we have this question is that we haven't seen any evidence at all of intelligent civilizations elsewhere. Not one shred. There's no exhaust. There's no exhaust from their matter-antimatter engines. We haven't seen obelisks on the moon or Mars as depicted in the movie 2001. Nothing happened to Jodie Foster where she was carried away to another planet. We don't see evidence of any sort of advanced technologies using energy 1,000 or 1,000,000 times more prodigiously than we humans are using energy. And of course, if they build spacecraft, indeed, they would wander here by chance, even if they didn't know about us, and they probably do. So why don't we see evidence of their visits, their transmissions, their spacecraft, and so on? So this has led to something called the Fermi Paradox. And the basic idea is, could we, in fact, take advantage of the lack of detections of intelligent life and construct plausible theories by which intelligent life is less common than the science fiction writers and my own calculation suggested. Could it be that we humans are more rare as an intelligent phenomenon than we give ourselves credit for? And there are a few ways that we could have blown it. One way is maybe the Earth, yes, is a habitable planet, but other Earth-sized planets are different from the Earth. And one way is water. You see, the Earth we think of as covered with water, but actually the oceans comprise a droplet of water that spreads out like a thin veneer over the surface of the Earth. And this tiny droplet of water begs the question, what if other Earth-like planets form with, let's say, less water, half as much, a half a droplet or a third of a droplet? Well, in that case, the water would soak into the interior of those rocky planets like a sponge, and the surface of that Earth-sized planet could be bone dry. Now, you might say, well, that sounds oddly pessimistic. You know, why should Earth-sized planets be bone dry? That doesn't seem possible. Well, look at the two planets on either side of our own Earth. To the left of us, Venus, no water on the surface. To the right of us, Mars, bone dry as well as cold on the surface, no liquid water on Mars. So we have evidence right in our backyard of two perfectly normal Earth-sized planets, rocky indeed, that have no liquid water on the surface at all. So this is plausible. It may be that our Earth with liquid water on the surface is a rarity. It's also possible that some Earth-sized planets acquire in their formation 3 droplets of water, or 5 droplets, or 10 droplets of water, in which case those Earth-sized planets would be, well, to be generous, like a bad Kevin Costner film. And of course, the microbes would flourish on a water world. The fish, the birds might, maybe even marine mammals if they somehow became mammals without land. But how could an advanced civilization develop electronics, grand pianos, rocket ships, any of the attributes that we associate with culture and technology on a water world? Seems very much more challenging to build radio telescopes and spacecraft on a water world. So there may be advanced intelligent critters socially, but whether they actually develop technology would be much more challenging. It could be that our Earth is a 1 in 1,000 or 1 in a million itself in ways we don't appreciate. Another way that we humans might be a rarity in the galaxy is, it's interesting, we now all know about Darwinian evolution. We understand that critters started as single-celled life, evolved into multicellular life, and became more and more complex and more intelligent. We like to think of ourselves, Homo sapiens, as residing at the pinnacle of the Darwinian evolutionary tree. We're the end product, the inexorable end product of evolution. But actually, the fossil record disagrees. The evolutionary biologists can tell you that most species on the Earth live for not just millions, but even tens or hundreds of millions of years, and their intelligence doesn't increase. From the cockroaches to the dolphins and all the species in between, they find a niche, they survive in ways that don't require bigger and bigger brains. And there's no better example of this than the dinosaurs. They roamed the Earth and ruled the Earth for 150 million years, much longer than we humans have been around. We've only been around for a few 100,000 years. The dinosaurs had plenty of opportunities. You know, dinosaur egg laid and baby born after dinosaur egg laid and baby born, for the smart dinosaurs to outcompete the low IQ dinosaurs and therefore pass on their intelligence genes to the next generation. That didn't happen. Dinosaurs, as we all learned in second grade, had brains the size of walnuts. They had intelligence similar to that of chickens. No criticism intended to the chickens. But in fact, birds, as you know, are the descendants of dinosaurs. This shows that we humans enjoy an encephalization, which is the word the biologists use, brain size to body mass, that is a quirk. It is not the case that other species get smarter. Occasionally, yes, but mostly no. And so it might be that it takes not 5 billion years, as was the case for humans, to pop into existence, but typically it's 15 or 20 billion years. Planets come and go and never develop critters that can play chess or, write piano concertos. I always like to remind myself that not only did the dinosaurs not get smarter, but even our mammal friends don't really get that much smarter. Bugs don't do algebra, and cats, YouTube aside, don't play the piano. So it's interesting that we humans have something special, a proclivity for speech, a dexterity for tools, and high intelligence. And then finally, maybe technological civilizations are rare for a reason that we all know about. Once you have intelligence, you develop technology, and eventually you gain the ability to threaten your own existence, either with weapons of various sorts, biological, chemical, nuclear weapons, or for the first time in our own history, the capability of altering your global ecosystem, your global environment. Our generation is the first one that is changing the atmosphere and the oceans of the Earth globally. And so we're entering new territory. That will happen to any technological civilization. And so there is a question as to whether or not intelligence is its own undoing, and the lifetime of an intelligent civilization might be short. Perhaps our galaxy had intelligent civilizations, and they winked on, blinked on and blinked off, like, so many lights on a Hanukkah bush. So it's a worry that maybe intelligence is rare, not because it doesn't form, but because it has a limited lifetime. So I will finish with this. It's an amazing era, in my view. We are in an era that reminds us of the Apollo discoveries, the discovery of penicillin, the internet, and so on, but in the planetary domain. We're detecting the first Earth-sized planets. They're common. Many of them are rocky. They are in the habitable zone in many cases with lukewarm temperatures. If you took a poll of molecular biologists at Stanford or Berkeley and you asked them, do you think on a rocky planet with liquid water, DNA might spring forth from the amino acids that are already there, they would say, how could that not happen over the millions and billions of years where the chemical experiments keep going in the oceans? So it's probably true that there are single-celled bacteria ubiquitous within our Milky Way galaxy. If you had to guess, you'd guess that the smallest critters are common. But intelligent life, we still don't know. The jury is out. We have evidence for in the form of all the planets, evidence against in that we just don't see any evidence of the intelligent life so far. And I'll finish by saying that we're looking. We have some very serious efforts to pick up the radio signals from another civilization, television broadcasts, maybe the laser beams from their galactic internet, if there is such a thing. And so there's a chance that in our lifetimes we'll answer this question as to whether or not we humans are alone in the galaxy. So I'll stop there. Thanks.
We'll have microphones on both sides of the aisle, and our first question, I think, is right here.
What ingredients other than liquid water are actually necessary for life?
What do you think?
I'm not sure.
Neither am I. Well, I'll tell you, you said it in just the right way. The ingredients for life, we actually have some sense of it from the biology here on the Earth. You do need liquid water. Why? Because water serves as the mixing agent, the way that molecules that are based on carbon, organic molecules we call them, can break apart when they're in liquid water and then recombine in new forms. So you have methane and ammonia, other ethane alcohols, if I may say, that can break apart in water, reform into more and more complex carbon-based organic molecules, eventually reaching something that looks like DNA, presumably. And so the second ingredient is carbon-based molecules. That's easy because carbon is a common atom in the universe. Another ingredient, by the way, is energy. You need something to sort of heat or spark the water with those carbon-based molecules in there to help them break apart and then maybe recombine somewhere else. But of course we have heat here on the Earth. There's geothermal energy, there's the sun, there's lightning, many heat sources, energy sources to power the biochemical reactions that might lead to life.
Next question in the front row.
I have a question about how much do you feel that science is going to be impeded from future discoveries in this country by the general atmosphere of non-scientific forces?
Yeah, I get the drift of your question, and of course we're all aware that there are certain political parties that are less comfortable with some types of science than perhaps they should be. But I will tell you this, to be very honest, and I'll be direct. In the United States, both the Democrats and the Republicans, it's the actual truth, are strong supporters of this kind of science. They're strong supporters of NASA, perhaps for dubious reasons, the geopolitical stature that comes with NASA. They support the National Science Foundation in ways that don't threaten perhaps their political views or religious views or whatever. So this kind of research, we're very well supported, both, by the way, from the public sector, that is to say the federal government, and the private sector. There have been many donations from people who have the wherewithal to help our research, and they do fund the construction of telescopes and the instruments, and even fund the salaries of graduate students who are learning the way.
Question right here.
Thank you, by the way, for taking the time to cross the bridge and be with us tonight. I know how busy you are. Two quick questions. One, in your animation, where you talk about how the planets transit across the star,
Yeah.
but that assumes that the way Kepler's aimed at them, that they're at the same axis and plane. What if they're tilted, and does that obscure, or how do you clean up for the data? And the second question is, the same calculations that you've done for the distribution of Earth-sized planets and habitable zones,
Yeah.
have they extrapolated that for the potential intelligent lives and like the distance they would travel if they were one of those early intelligent civilizations? Did they extrapolate the same, math to say, okay, assume they could travel speed of light, the
Yeah.
soonest that could hit us
Yeah.
would be X?
So these are two great, wildly great questions. I will try to keep the answers confined, but we could have a good time talking about this for an hour. First question. What you said is absolutely right. If you have a star, the Kepler telescope will only detect planets that reside in an orbital plane that happens to be seen edge-on from your position at the Kepler telescope. If the planet crosses in front of the star, we see it. If the orbital plane is tilted 20 degrees, 40 degrees, 60 degrees, maybe even a face-on orbit, Kepler won't detect them at all. We took that into account when we computed this 1 in 5 number. One of the corrections is a geometry problem from 10th grade. For every planet that you detect in an edge-on orbit, how many planets must you therefore have missed because they were in tilted orbits? So that's accounted for. Now, your second question, I'm going to rephrase it for everybody because I think I know exactly what you're talking about. If there are technological civilizations out there, they would surely develop propulsion systems, spacecraft. There would be some level of curiosity, maybe not every single century, but eventually. And they would travel to the stars to some extent. And your question is, traveling at some speed, let's say the speed of light, or maybe even a tenth the speed of light, how quickly would those civilizations migrate and populate the rest of the Milky Way galaxy? And the answer is very interesting. It's a blink of an eye, it turns out. That is to say, the age of our galaxy is about 10 billion years old. 10 billion years old. It only takes a few tens or hundreds of millions of years for a spacefaring civilization to migrate and populate the galaxy, much the way we humans started on the East African savanna and populated the whole globe of the Earth. So that makes the absence of obelisks and matter-antimatter engines, the absence of any evidence of advanced civilizations, indeed, inhabiting the Earth, having come here to enjoy the Earth, their absence seems profound.
Question over here.
Yes, I read a Scientific American article that inferred that we're doing analysis of light coming through the edges, the atmospheres of exoplanets. And I assume it's spectrographic, but have you got, but the article was that we can find things that are in the atmospheres. We can find the compositions of the atmospheres. You're nodding. This is true?
It's absolutely true. It's a very exciting subfield of planet research. What people do is very simple. If you have a star, and as we've said, the planet crosses in front, some of that starlight will come to the Earth by passing through the atmosphere of the planet, and some of it will be absorbed by the molecules in that atmosphere on their way, the photons, toward the Earth. And so the light that we receive, as you said exactly right, spectroscopically, we'll see the light that got absorbed by that planet's atmosphere, and that light will be missing certain colors or wavelengths of light due to certain molecules like methane, ammonia, water. There's one carbon monoxide and carbon dioxide. Oxygen, if it's there, will absorb the light, and we'll see that in the spectrum. And people are doing this, and they are detecting methane, ammonia, carbon monoxide, and dioxide. Yeah.
Next question.
There's actually more to it than, how far down can we detect? So we have an atmosphere of ours that would be mostly nitrogen.
Yeah.
You'd see it from if you've got your Kepler on some distant, star, or
right.
some distant star, you look at the Earth and you say, oh, there's a lot of nitrogen on there.
Right.
Can you detect the oxygens? What, 22%?
Yeah. So let me just put a little bit of a wet blanket on your question because it's such a good one, but there is a challenge. Planets the size of the Earth have a little tiny thin atmosphere, and so far nobody has been able to analyze the chemical composition of an Earth-sized planet around another star. And that day may come with a new telescope in space called the James Webb Space Telescope, still a few years away.
Next question on your right.
In the first Kepler 10 light graph that you showed,
Yeah.
there were these gaps in between the bundles of light. What were the gaps?
That's where President Nixon erased the data.
Can you show it? Can you show the graph?
I don't know if I can really go back through all of the slides. I guess I could get out a PowerPoint and do it that way. If you really, really, really want to see the missing data, clearly suspicious. So what happens is there are two reasons for the gaps. Some of them are fairly regular, and that's because, this is the truth, there was a budget consideration in the construction of the Kepler spacecraft. They took away the antenna. Yeah, NASA felt that we were over budget and we couldn't keep the antenna. Why is that important? The antenna would have transmitted the data back to Earth, allowing us to stay fixed on the Cygnus constellation. Because we had to get rid of the antenna for budget reasons, we had to turn the Kepler telescope, point it toward the Earth, download the data, and then turn it back to take data. So there are gaps whenever we're downloading data. The other reason is some of these gaps occurred because the spacecraft failed electronically for a few hours or days. You know, there's some glitch in the computer system or the electronic system that's called a safe mode. We can't take data, comes back online, and we begin taking data again.
Question right here.
On this question of the incidence of intelligent life, you know, in the universe in general, where do you know, I hear all the, you know, the different sets of logic and so on, the different arguments. Where do you net out on all of this?
Well, if you really, you know, force me to give my opinion, the Milky Way galaxy has 200 billion stars. There are hundreds of billions of planets. But I think it's a serious absence. And many of my colleagues don't agree with me, so I should be very clear that I represent one group that has a point of view. There's another group that would argue with me. I think the absence of any clear signs of technology out there suggest the following: that we humans as a technological civilization are rare. Clearly there are other advanced intelligent civilizations out there. If you include the other galaxies, there are hundreds of billions of galaxies like our Milky Way. So it would be foolish to suggest that we humans are alone in the universe. But within our Milky Way, maybe we're one of 5 current advanced civilizations. Maybe we're 1 in 30. But we probably are rare enough that it explains why we still to this day don't see any signs of them. That would be my guess.
Question right here.
Thank you for a great talk that even non-scientists can enjoy. You mentioned a Swiss colleague, but that was the only time you mentioned any international collaboration. And I just wondered, what's the level of expertise in other countries with scientists in China, Russia, and are they contributing to the huge amount of knowledge that we need to generate in the future?
Yeah, thanks for that question. There's a tremendous amount of activity on the search for planets around other stars and characterizing them in Europe, France, Germany, the Max Planck Institute, Geneva, Switzerland. The UK has many exoplanet hunters who are doing beautiful work. Spain. And so it's flourishing. There are thousands of exoplanet, as we call them, experts in Europe. China has a growing number. I've been to Beijing several times. They're building telescopes. Japan has active research. India now has active research. South Africa has a lot of research. So the study of planets around other stars is now a global activity.
Next question.
You gave us a chart showing, or illustration showing approximately 400 planetary systems in the Milky Way galaxy, and mentioned that there aren't enough astronomers to study all the systems. Yes. What selection criteria would you give to your graduate students for picking one to study?
You know, this is a great question, and I mentioned that one of my students, Lauren Weiss, is studying Kepler 11. And in her case, she selected it herself, which is the best possible way for a graduate student to go. Her inquisitiveness, her curiosity, and her sense as to a system of planets for which there were measurements in hand and that she could acquire might allow us to learn a significant more information about that multi-planet system. So she constructed the project herself, and is pursuing the acquisition of data. So the best of all worlds is when a student, is self-motivated and initiates the project themselves. But of course, for younger students, that's my job as a professor, to sense which of the systems has such attributes suitable, amenable to further study, acquisition of data, maybe some theory or some modeling. So, there's an interplay between myself and students as we decide what projects they might work on.
Question over here.
You were continuously mentioning looking for Earth-sized planets. Is there something specific about the size that would dictate the chance of life?
Yeah, that's a great question. And here's a funny thing about our universe. As a whole, it's composed mostly of hydrogen gas, a relatively small amount of helium gas, and hardly anything else. And you might say, well, wait a minute, the Earth is clearly made of silicates, the rocks, magnesium, iron, silicon, oxygen, in the core iron and nickel. So why is the Earth composed of these heavier atoms when the whole universe is made mostly of hydrogen and helium? And the reason this is connected to your question is that the larger planets got to be large, like Jupiter and Saturn, by acquiring large amounts of the common elements in the universe, namely hydrogen and helium. So the big planets are all big balls of gas, hydrogen and helium. And only the smaller planets have a chance of being rocky. Even some of them may be mostly gaseous. But it's the small ones, we've measured this with density measurements, it's the small ones for which a good fraction of them are in fact rocky.
We'll take the last question right here.
The graph showing the percentage of stars with various sized planets didn't include an area for smaller than Earth-sized planets.
Yeah.
Is there a reason for that?
Yeah. The planets the size of the Earth, I didn't give you this number, but you may have inferred it. When an Earth-sized planet crosses in front of a sun-like star, it blocks only 1/10,000th of the disk of the star. And smaller planets, we wish we could detect them, but they get lost in the noise that you see here. Imagine a planet even smaller, 5 times smaller. It would get lost in the noise. The reason is that the Kepler telescope was only a certain size, about half the size of Hubble. A bigger Kepler telescope would acquire more light, the errors would go down, and we could detect smaller planets.
Thank you so much. Thank you, Professor Marcy.